All right, so let's go over a couple of examples with Maple. What I'm going to show you is essentially the simulation of rolling a die or tossing a coin repeatedly. So let me illustrate let me explain a couple of things uh, so you understand what you're going to see in this Maple presentation. So this function rand from randomize from 1 to 2 is essentially a random number generator, and it allows you to each time you run that function, it allows you to actually come up with a random number between those two numbers. So if I want to simulate tossing a coin, I can associate the 1 with the heads and 2 with the tails. So if we associate this rand between 1 and 2 to the coin, this is basically the name of my function. Each time you run this function, let's see. So each time you run the function coin, you're going to end up either 1 or 2 repeatedly. So randomly, obviously. So it basically simulates tossing a coin. So for example, I run it several times. Now it's 2, 2 again, 1, 1, 2 again. So it's going to be either 1 or 2, obviously, with probability 1/2. So let's go over the example that I did in the presentation. So let's say the game is that heads wins $2, T loses $1. So what I do here, basically, I initiate the number of tosses so I can keep track of the number of times I toss the coin, and the gain, which I initialize it with 0. And then in this command, each time I toss a coin, I'm going to increase the number of tosses. And then if it lands 1, if it's heads, I'm going to add 2 to the gain. If it lands tail, I'm going to subtract 1 from the gain. And I'm going to keep track of the gain and the number of tosses. So just to remember, the expected value in this case is going to be 1/2 times $2 plus 1/2 times minus $1. So it's $0.5. So like I said, initialize tosses and gain. Run it once. So notice the number of tosses is 1. The gain is 2 because I ended up with heads. So each time I'm going to run this applet here, this command, the number of tosses increases by 1, and then the gain changes its value depending on whether it's heads or tails. So for example, the gain is 9 now. I run it again. Because I ended up with tails, I subtracted 1 from the gain, so now it's 8. Run it one more time. Now I end up with heads. Gain is 10. One more time. Now it's 9. Heads again. Plus 2, 11. Tails 10. Tails 9, and so on. So let's do it 20 times. The gain is 13. So how close it is to the expected value? Well, 20 over 13. The other way around, sorry. So 13, the gain, divided by 20 is 0.65. So it's pretty close to the expected value. The more times you run the game, the closer you are to the expected value per game. So let's actually run it 40 times. Okay, so now the gain is 23 divided by 40. Now it's 0.57. So you notice it's actually closer to the expected value. The more times you run, the more likely you have to be really close to the expected value, unless you have a very weird situation in which you ended up with way too many heads or tails in the beginning. But if it's a true random 50-50 probability, then you should be closer and closer to the expected value if you divide the gain to the number of tosses. In this example here, I want to show you the opposite essentially. Let's say you win $1 if it's head, but you lose $2. So you should end up with pretty much the opposite situation. In other words, a loss, a net loss, because you stand to lose $2 as opposed to win $1 with probability 1. So if we run this game, let's do it 20 times. The gain should be negative, obviously. And actually, see, that's kind of weird. Actually, in fact, I end up precisely with -1/2, right? So if you divide the gain to the number of tosses, you end up with minus 0.5, which is the exact expected value in this case. We could do the same for rolling a die. Here I generate a random number from 1 to 6. So each time when I execute the roll function, that means rolling a die, so the value will be either 1, 2, 3, 4, 5, or 6. So suppose that, let's say in this game, I didn't actually write it down here, but let's say if you roll a 1, you end up with, you win $4. So that means the contribution in the expected value is 1/6 times 4, right? So the probability of rolling a 1 is 1/6. Then if you roll a 4, 5, or 6, let's say you stand to lose $1. Now the probability of rolling a 4, 5, or 6 is going to be 3/6. And for the other numbers, 2 or 3, let's say you don't gain or lose anything. So we don't even put them here in the expected value. So 1/6 times 4 plus 3/6 times -1, that's going to be 0.16 or 0.17 approximately. That's the expected value. And let's see what happens if you run the game several times. All right, so I didn't actually write down what the roll is, so maybe I should put it here so we could see what we get. Oops. I guess I need probably some syntax error. Okay, so okay, 5, we lost $1. I roll a 4, I lose another $. Now I roll a 1, now I win $2. So actually let's start over so we can see it from the beginning. So the first roll, I lose $1 because I ended up with 6. One more time, I roll a 2, the loss is the same, $1, because when I roll 2 there is nothing, no gain nor loss. 1, now I stand to gain $4, but remember I started from -1, so -1 plus 4 is gonna be 3. Okay, so let's run it. Let's do it 20 times. So the number of rolls, let's get up to 20. So let's see how close we are to the expected value. So we have a gain of 8, which if we divide by 20, the number of times we play the game, that's 0.4. So that's pretty good actually, because remember the expected value is 0.16. Let's actually run the game further. Let's do it 40 times. One by one. And the gain now is -6. We're pretty unlucky actually. So, but let's see actually how close we are. So -6, well, I mean, I guess it's not really, we had an unlucky streak on this one. -6/40. Let's make it a decimal here. I mean, it's close to 0, but it's on the negative side, right? Let me see if I do it, if I continue. The problem is that there are lots of opportunities to lose. So you really have to run the game lots of times to come ahead, especially if you're unlucky in the beginning. Let's do 70 times, and then below I'm going to show you thousands of times using, of course, commands so that we don't do it one by one. So yeah, it's still negative gain here because I had lots of instances of 4, 5, and 6. So here it's just the same example as before, but now I basically use commands in Maple to run it lots of times. So for example, let's say I run the game 100 times. The gain is 13, the first number is the gain, and the other number of rolls. So the gain over the number of rolls, 0.13, is pretty close to the expected value, 0.16. Let's increase to 200 number of games, of rolls, right? So the gain is 38 divided by 300, 0.12, kind of close. And now let's do a huge number. Let's say we run it 10,000 times. So in that case, we have a gain. We pretty much see we're very close to the expected value. 1,662 divided by the number of rolls. Oh, I actually didn't initialize the number of rolls, so let me start over. So I have to initialize it so that it's so it's 1580 the gain, and the number of rolls obviously 10,000. Make it a decimal. Very, very close to 0.16. Okay, so the more times you run the game, the closer you are to the expected value. So I encourage you actually to do this on your own with Maple. It's a fun exercise, and I suppose it will help you understand the actual meaning of the expected value and what actually it indicates. And that's it for today.